Hi there, this is Jude Socrates. Welcome to video number 32 for my series on multivariable calculus, known as Math 5C at Pasadena City College, where I will be teaching this class again in the fall of 2021. And hopefully we'll be back face-to-face, and I can actually see your faces for a change. So today we are going to continue with parametric surfaces. We're going to talk about partial derivatives for these parametric functions in two variables, and we're going to construct the tangent plane to these surfaces. So I will see you on page number 265. Okay, so in the last chapter, when we did parametric curves, we did something very similar to this. We had a function r of t, and it was x of t, y of t, z of t. And then we took the derivative. Okay, so we called it r prime of t, x prime, y prime, z prime. But now we have a vector equation, a vector function, in two variables, two input variables, u and v. So therefore, we can't talk about just ordinary derivatives. We're going to talk about partial derivatives. Okay, so let's assume that the domain is some rectangle, and that all three components have continuous partial derivatives. Okay, so therefore we can make the symbol partial of r with respect to u, and we can just call that r sub u, and it's just the three partial derivatives. Okay, so partial of x with respect to u, partial of y with respect to u, and partial of z with respect to u. Okay, and similarly, of course, for the partial derivatives with respect to v. All right, so we saw partial derivatives way back in chapter 2 because we had to understand the concept, the reverse concept of partial antiderivative. Okay, so we haven't exactly been playing around with partial derivatives too much. Okay, so what's the idea here? If you have a function in two variables and you want partial, in this case with respect to, say, u, then you keep v constant. Okay, and then you just take the derivative with respect to u, just like you do in single variable calculus. Okay, so now that we have a parametric surface, let's fix a point u0, v0 somewhere in the domain D. Okay, so right now we have a rectangle. Okay, so pick a point inside the rectangle. So let's think about partial derivative with respect to u. Okay, so what we say, fix the other variable v constant. Okay, so let's call that constant value v sub 0. Okay, so we have r of u v sub 0. Okay, so that's only going to depend on u. So let's give that a name. Let's call that r1 of u. Okay, so that means x at u v sub 0, y at u v sub 0, and z at u v sub 0. Okay, but now since this is one variable, u, where u is from a to b, what do we get? We get a space curve. Okay, and of course that space curve will be entirely on S. Okay, so we're going to do the same for v, so let's call that space curve C1. And so the partial of r with respect to u, when we evaluate at u0, v0, is simply the derivative with respect to u of r1 of u, this new function, where we plug in u equals u sub 0. Okay, but we were just talking about tangent vectors. Okay, so r1 of u gives us a tangent vector to c1 at the point u0, v0. Okay, so of course we're going to do the same thing for partial of r with respect to v. So this time we will fix u to be u0, and we will restrict r so that u is u0. V can be any number from c to b, the domain for v. So we get a function only in v. We'll call that r2 of v. And it's just like r1 of u, except this time it is the u coordinate, which is constant at v sub 0. Okay, So R2 of V creates another curve, let's call that C2, which is also an S. And so the partial of R with respect to V, evaluated at U0, V0, is just the ordinary derivative of R2 of V, where V is set to V sub 0. So we get the tangent vector to C2 at this same point, U0, V0. Okay? So that might seem a little abstract to you, so never fear. Let's see what happens when we apply all of this to a sphere. We have nothing to sphere but sphere itself. Okay, let's move on. Okay, so here's a sphere of radius 4. We know how to parametrize that using spherical coordinates. U will go from 0 to pi, V will go from 0 all the way to 2 pi. Okay, let's pick a point. Okay, so the problem with pi over 6, pi over 4 is that you get square root of 3, so it's ugly. Okay, so let's pick angles expressed in inverse, in this case, inverse cosine, so that at least we'll get fractions. Okay, so let U0 be inverse cosine negative 3/5, and V0 will be inverse cosine positive 12 over 13. Okay, so you know your trig. The cosine of this angle is simply minus 3/5. Complete the triangle. We know the sine is positive 4/5 because we're in the second quadrant, okay, where the sine is positive. Okay, so similarly, complete the triangle for 12 over 13. So the cosine is 12 over 13. The missing side is 5. We're in the first quadrant, so the sine is also positive 5 over 13. Okay, so if you plug that into our parametrization, we're going to get these coordinates. And it looks nice to have them all with the same coordinate. Okay, so let's write it as 192 over 65, 80 over 65, and negative 156 over 65. Okay, so just in case you're doubtful of my arithmetic, and I don't blame you, plug them into the equation of the sphere, and you will get 16. And I did use a calculator on that, so you can trust that to be 16. Okay, so what are these C1 and C2 that we were talking about in the previous page? Okay, so we will keep V constant at V sub 0, inverse cosine 12 over 13, and we will construct a parametrization where we only see the variable u now. Okay, so that is a space curve, and similarly replace u with u sub 0, inverse cosine negative 3/5, and we get this parametrization where we only see the angle v. Okay, so in particular the z coordinate is always negative 12 over 5. Okay, so let's review spherical coordinates. Okay, what does it mean for phi to be constant? What does it mean for theta to be constant? Okay, because u represents phi and v represents theta. Okay, so here we kept theta constant. So remember, that's like a swinging door. Okay, it's a half plane where the angle that that plane makes with the positive x-axis is inverse cosine 12 over 13 in this case. Okay, so what does that, how does that intersect the sphere? You get a semicircle passing through the north and the south poles. Okay, so what you might call on the globe a longitudinal line. Okay, what about if phi is constant, which is the v? Okay, so notice how we got a constant z coordinate. That's because we get a circle going around the z-axis, and we get a latitude. Okay, so that circle is always at the plane z equals negative 12 over. All right, so we got the sphere over here. We have two views of the sphere. Here is the longitudinal line corresponding to a constant theta, and here is a latitudinal circle, okay, corresponding to constant phi. Okay, so of course they intersect at the given point. Okay, so we get those two curves. Okay, so now that we have those curves, okay, we're ready to get the partial derivatives. Okay, so I'm taking you back to where we have the parametrization. If you have a piece of paper and a pen, let's do this together. Okay, so let's take the partial of r with respect to u. All right, so we have these here, pretend they're constant. We're only taking the derivative with respect to u. Okay, so 4 sine u cosine v, that becomes 4 cosine u cosine v. And then we have 4 sine u again sine v. So that is also 4 cosine u sine of v. Okay, so the v does not change. 4 cosine u, take the derivative with respect to u, we get negative 4 sine of u. Okay, so I hope you wrote that down. Okay, so next we want partial with respect to v. This time the u's are constant. Okay, so 4 sine u is a constant. And then cosine v, that turns into negative sine of v. Okay, 4 sine u, that is a constant. And then sine of v turns into cosine of v. 4 cosine u becomes 4 sine, no, haha, just kidding, because our u is a constant. Okay, so that turned into minus 4 sine u for partial of r with respect to u, but with respect to v, that's just a 0. Okay, so let's go to the next page and see if we got the answers. Okay, 4 cosine u cosine v, 4 cosine u sine v, negative 4 sine u, woohoo, minus 4 sine u sine v, 4 sine u cosine v, and 0. Okay, excellent. We know how to take partial derivatives. Now, let's plug in the actual values of cosine u0, sine u0, cosine v0, sine v0 into these two partial derivatives. Okay, so we got these fractions over here. Simplify. Again, let's put all over 65 so we can compare apples to apples and not oranges. Okay, same thing for partial of r with respect to v at the given point. Okay, and we are ready now. We are ready now to complete the picture with these two tangent vectors. Okay, so, okay, who was the red one? That was the one with the constant theta, so that's the constant v. So it's the partial with respect to u, this one. Okay, and yes, because the z-coordinate here is negative, the vector is pointing down. Here the z-coordinate is 0, it's just staying level. Okay, so that is the partial of r with respect to u at that point, and this is the partial of r with respect to u at that point. Alright, so I have a copy of those three tangent vectors again, but now the important thing is they pass through the same point and they're not parallel to each other. Okay, they're definitely not pointing in the same direction. Okay, so what have we got? Go back to the first section, the one we just did, and you have a point and two vectors which are not parallel to each other. You can create a parallelogram with those two vectors anchored at that point, and we know how to do it using the surface command. Okay, so we get what is called a tangent plane to the sphere at that point. Okay, so our next job now is, well, that's great. I know how to do it using surface, but what about a Cartesian equation? Okay, so we're going to need a normal vector, and of course, how do you find a normal vector from two vectors? We're going to take their cross product. Okay, so I hope you remember that we called a parametric curve smooth if the tangent vector is never the zero vector. Okay, so analogously, for a parametric surface, we will say that the surface is smooth if the tangent vectors at that point are not parallel to each other. Okay, so first of all, they can't be the zero vector. Game over if one of them is the zero vector, because the zero vector is parallel to all vectors. But just as important, they can't be parallel to each other. Why? Because if they're not parallel to each other, we can find their cross product, and then that vector will be a non-zero vector. Okay, so therefore, once we get that cross product, we can find the equation of the tangent plane to the surface at that. All right, so here are our two tangent vectors. We can ignore the 65s. That's just constant, because all we need is a non-zero direction vector, a normal vector. Okay, so we can ignore the 65s. All of these are divisible by 4, or in this case, -4 would be better. And both of these are divisible by 16. Okay, so we can take these two smaller vectors, take their cross product. Trust me on this is what we get. But also, miraculously, this vector is divisible by 13, and we get a much smaller vector. Okay, so we are ready to find the equation of the tangent plane. Set it up over here. Plug in the points, the given point, and this time we're not allowed to clear the denominator. Okay, so the 65 is part of the point. Okay, but fortunately we get a whole number, -260. Okay, so we can make it look nicer by multiplying by -1. Okay, so this way we only have one negative number. Okay, so for our problem today, we are going to play with the same sphere, but we are going to rearrange the point. Okay, so let me take you by choosing the theta and the phi, basically. Okay, so we got these three coordinates, and we checked that they do satisfy the equation of the sphere. Okay, so what am I going to do? Okay, well, it's x squared plus y squared plus z squared equals 16. Okay, so it doesn't matter what order these three numbers are, and it doesn't matter if it's plus or minus. Okay, we can play with the signs as well. Okay, so I decided I am going to make a new x coordinate of 156. I'm going to move this over, make it positive 156 over 65. I will scoot the 192 to the middle, and we'll have minus 192 over 65. I will change it to minus. I will keep positive 80, but move it over to the right. Okay, so we made musical chairs. Okay, I moved the z over to the x to the y to the z, and I changed a couple of signs. So, time to go to our workroom, and we're going to find the tangent plane at that point. Okay, so this will be our problem. Find the equation of the tangent plane to the sphere, same sphere, at the point 156 over 65 minus 192 over 65 and 80 over 65. Okay, so that gives us an opportunity to review our parametrization and our partial derivatives one more time. So our parametrization was 4 sine u cosine v, 4 sine u sine v, and 4 cosine of u. Okay, so what are our partial derivatives? We said it was 4 cosine u cosine v, 4 cosine u sine v, and -4 sine of u. And the other partial derivative was -4 sine u sine v, 4 sine u cosine v, and 0. Okay, so yeah, let's label this is our r sub u, and this is our R sub v. Okay, and of course this is the parametrization itself. Okay, but wait a minute. Who is the U0? Who is the V0? Okay, so this is where your trigonometric skills come in. Hopefully you'll know what to do. Okay, we need to solve for U and V. Okay, so I do believe that the Z coordinate is simplest because we have one variable. So 4 cosine U must be 80 over 65. So what does that mean? Cosine U is 20 over 65. And yeah, we can reduce that for now. It is 4 over 13. Okay, so we also need to do the same for sine of V. Or, of course, we can also get it from cosine V, but let's see what happens. Okay, so solving for the second coordinate, we want that to be equal to this. So set them equal to each other. And again, we know that sine of U is over here. So we can replace sine of U with this. Okay, and what have we got? Let's make a copy. Again, 13 cancels with 65 partially. We get 5. What is 192 divided by 4? Let me do that over here. Since it is set up already, we get 48. Okay, so we get sine of V is 48 divided by 5 square root of 153. Okay, and of course we can check if we square these two and then add them together, we better get 1 exactly. Okay, cosine squared plus sine squared had better be 1. Bingo, we got 1. Okay, so we are ready for the partial derivatives. We are going to plug in these 4 values into our partials. So cosine U are up, so we need 4 over 13. You know what, let me just write 4 over 13 here, because the rest are in one line. Cosine V is this, so that goes away. 4 cosine U, so we have this. Sine of V is this, so we replace with that. Minus 4 sine of U, so we have this. Okay, there we go. So, we have this ugly radical 53 in the denominator, but fortunately, it's in the numerator over here, so we can make it go away. So first, let's simplify. What do we got here? Okay, very nice. Now, remember, we are going to take cross products, okay, because we want just the direction of the normal vector, okay? So we can certainly get rid of the square root of 17, okay? So instead of putting equals, okay, so we will use instead for the cross product, okay? We're going to take this vector, reduce it, okay? So first, square root of 17, go away, and we get this, okay? Is 1105 the LCD of the 3 denominators? One way to find out, multiply everyone by 1105, and yes, they all go away. Oh, but wait a minute, now that looks like everyone is divisible by 4, right? You know what? How about compute and factor? Oh, yes, yes, we do have 4s everywhere there. Okay, magic trick. So divide by 4, we get, uh, what do we got? Okay, there we go. I don't think that can be reduced any further. Okay, so the same thing, we're going to find partial of r with respect to v at that point. So what have we got? Sine of u over here, and it's in 2 places. So let me be efficient. I will put it here, and I will put it over here. Okay, sine of v, we only got one of them, and we got this. Okay, cosine of v, we got this. Okay, great. So, yeah, so this time the radical 153s cancel out naturally. So there we go. We got 192 over 65, 12 over 5. And of course, we will use instead, take this vector, multiply it by 65. And what have we got? Okay, over here. And I think there's also 4 in there. Is there a 4 in there? Yep, and that's about it. That is the best we can hope for. Or is, oh, wait, there's a 3. There's a 3 in there. So over 3, yeah, 16 and 13. Okay, excellent. So now we take the cross product of the 2 vectors, and I'm sure you remember how to do a cross product, right? So, cross, and this, I don't think I've ever done this before with you guys. Ooh, yeah, look at those big numbers. What can we take out? Compute, factor, ooh, oh my. 3s, no, just 5s, and 17s. Oh yes, oh look at that. 5s and 17s. So divided by 17, and we get this, divided by 5, and we get this. Okay, 39, and anything else there? No, 13 times 3, no. That's about it. Okay, so that is our normal vector. Okay, so normal vector to the plane is this. And so we can get the equation of the plane. Okay, 39x minus 48y plus 20z is equal to, oh, we need the point. The point is over here. Okay, and remember this time we cannot ignore the 65s. Okay, so let's put the point here. Copy that to the right. Multiplied by 156 over 65. 48 times y. Y is minus 152 over 65. And z is 80 over 65. Okay, so that becomes 260, yay. Alright, so I have plotted the point that we are given on this sphere, and we can check that that blue dot really is on that sphere. I have entered the equation of the plane because who knows, I might have made a mistake. Never happened to me, right? So let's see. There's our tangent plane, and yeah, it looks like it's just kissing the sphere at exactly that one point. Okay, so yeah, you might think that that is the definition of a tangent plane. It's not. Okay, the actual definition of a tangent plane is, and there's some little bit of hand waving here, It's the plane that best approximates the surface at that point. Okay, so in other words, if we zoom in at that point, closer, maybe turn a little bit. Okay, there you go. Okay, so notice how the surface and the plane, yeah, it almost looks like, yeah, if the Earth were flat, okay, and some people still think that it is, then the part of the Earth at that point should be just like that plane. Okay, so that is a rough, more ironically, it's rough. It's a rougher meaning, but it's actually closer to the reality. Okay, as I'm about to show you in an example. All right, so let's take a look at the Cartesian surface. All right, so we have this polynomial in x and y. We'll restrict it to this domain. And we will turn this into a parametrization. Okay, so u, v, turn x into u, y into v, and we get this for our z. Let's pick the point negative 1, 2. So negative 1 is in here, 2 is in here. Okay, let's find the partial derivatives. Okay, so with respect to u, 2 will go down, so you get 2 over 10, 1/5, u times v. U will disappear, minus 3 over 20 v squared. Okay. Partial with respect to v. Oh, I'm sorry. I forgot that there's a u and a v there. So u becomes 1, v becomes 0. Whoops, we do have 3 coordinates. Okay. Now, partial with respect to v, u becomes 0, v becomes 1. And then with respect to v, that v disappears. We get 1/10 u squared. That 2 goes down. So cancel with the 20, minus 3 over 10, u times v. Okay, so I believe next we are going to plug in the coordinates of that point. All right, so plug in negative 1, 2 into our partial derivatives, which is on the next in the last page, but it does simplify to these 2 vectors. Take the cross product, you'll get 0 plus 1 right there. And then 0 minus 7 over 10 there, and then 1 minus 0, you'll get 1. Okay, so that's not the 0 vector, that's our normal vector to the tangent plane. And, oh, we need the z coordinates. Okay, so plug in minus 1, 2, we get the z coordinate of 4/5. Okay, so we're ready to plug in the equation. X minus 7 over 10y plus z, we have that. Plug in negative 1, 2, 4/5, we're going to get negative 8/5. Clear the 10 in the denominator, you'll get 10x minus 7y plus 10z equals negative 16. Okay, and this is what I really wanted to show you. Okay, so these are the graphs that we got from the first section, okay, where we did the Cartesian, the parametric surface expressed from Cartesian coordinates. And here's the plane, the tangent plane. Okay, so notice that it doesn't quite look like it's just kissing the surface at that one point. Okay, as a matter of fact, they're cutting each other. Okay, so notice how you get these points, which are in common to both the plane and the surface. Okay, so it's wrong for us to think that a tangent plane can only intersect a surface at exactly one point. Okay, that is obviously absolutely not true in this case. All right, so for the rest of the section, we're making some generalizations. So what happens when you have a Cartesian surface parametrized like this? Okay, so we have u, v, and then g of u, v, but more naturally, whoops, that should be an xy. What if we have r of xy equals this parametrization? Okay, so when you take the partial with respect to x, that turns into a 1, y goes away, and we have partial of g with respect to x. Repeat for partial of r with respect to y, x becomes 0, y becomes 1, and then we get partial of g with respect to y. Okay, take the cross product. That's why we put them on top of each other. Cross product, so we get 0 minus gx right there, and then 0 minus gy right there. 1 minus 0, you get 1. So the z-coordinate is always going to be positive 1 in the cross product for this kind of parametrization. Okay, we have minus gx minus gy respectively in the x and y coordinates. Okay, let's generalize what we saw for spheres. Okay, so if the sphere has radius rho centered at the origin, this is our parametrization, phi from 0 to pi, theta from 0 to 2 pi. Okay, we know how to find partial derivatives with respect to phi, with respect to theta. This is exactly the same as what we had before, except we have now rho as a constant. Okay, so we are going to take the cross product of those two, and something amazing happens. Always. Okay, so we get for our x 0 plus rho squared sine squared phi cosine theta, first coordinate. For y, plus rho squared sine squared phi sine theta, that's our y. For z, rho squared cosine phi sine phi cosine squared theta. There are two cosine thetas. Minus, oh wait, not minus, plus, because we have a minus minus. Rho squared sine phi cosine phi sine theta sine squared theta. Okay, but something amazing happens in the z coordinate. Okay, so notice that we have cosine squared phi theta sine squared theta, and the other two are common. Okay, so we can factor that out, and that becomes 1, of course. Okay, so we have rho squared sine squared phi cosine theta, rho squared sine squared phi sine theta, rho squared sine phi cosine theta. Am I repeating myself? I seem to be repeating myself. Rho squared is everywhere. Sine squared, no, just sine phi is everywhere. Okay, so we can factor those out. Rho squared sine phi, where have I heard that before? Okay, that is the extra factor that we have to put in when we're doing triple integrals in spherical coordinates. Okay, it's not an accident that it shows up, because that is what we call the Jacobian of a change of variables. Okay, and we get this. All right, now there's something else which is interesting about this vector. Okay, we're still here. I needed to stay here because I need to compare this with our original parametrization. So I shrank the PDF a little bit so that it will all fit in one screen. Okay, so what do you notice? Sine phi cosine theta, sine phi cosine theta, sine phi sine theta, sine phi sine theta, cosine phi cosine phi. So this is the same vector except we're missing a row. Okay, so we can put one of the rows back inside there, and we have exactly the parametrization. Okay, so what does that mean? If you have a point on the sphere, it is the end point of this vector from the origin. Okay, the normal vector is the same vector practically. Okay, except there's an extra row sine phi. Okay, so basically the normal vector is parallel to the position vector. Okay, now we can move on to the next page. Okay, that's what it looks like. Okay, so I removed most of the sphere so that we can see the position vector, and I shrank the normal vector just a little bit. Okay, so this is a general principle from geometry. Okay, the normal vector to a point on the sphere is parallel to the radial vector from the center of the sphere. Okay, so in other words, if you draw the radius from the center to the sphere and you just keep going, what you get is a normal vector to the sphere at that point. All right, so I said there was a couple of interesting things about this vector. And this is the second one. Okay, so we're going to give that vector a name, n phi theta. Okay, n for normal. Okay, but there's also something interesting about the length of this vector. Okay, so square, square, square. Add them together. Okay, what can we bunch together? So these two have sine squared phi in common. Ooh, cosine squared theta plus sine squared theta sounds familiar, so that's equal to 1. And we have cosine squared phi along for the ride over here. Oh, but sine squared phi plus cosine squared phi, that's just equal to 1. Okay, so that's a unit vector. Okay, and this will be our notation in the fourth section for the unit normal vector to the surface at a point. Okay, so this portion of that cross product is already a unit vector, which means that the length of the cross product is rho squared sine phi. Okay, because from the properties of vectors, okay, if you have a vector and you multiply by a scalar, the length of that vector is just the length of the vector times the absolute value of the scalar. But what's the absolute value of rho squared sine phi? Rho squared is already positive, take it out. But where is phi? It's between 0 and pi. Sine of phi is positive for 0. Okay, so therefore the absolute value is just sine of phi. Okay? I lied. There's one more thing about this normal vector. Okay? And it has to do with the poles. Okay? When we first talk about spherical coordinates, we said that when phi is constant, we get a cone. Remember that? Except for 2 points. When phi is 0, you don't get a cone. You have a half line. Okay? And when phi is pi, you have the opposite half line. Okay? You don't get a cone. All right? So we have a similar problem with this vector, this cross product. When phi is 0 or pi, the length of that cross product is 0. Sine of 0, sine of pi is 0. Okay, how many vectors have 0 length? Exactly 1, the 0 vector. Okay, so this cross product is actually 0 at 2 points on the sphere. Not gonna lie to you. Okay, so the sphere is technically not smooth. It sounds weird, right? The sphere is perfectly smooth everywhere. You know, you have like this crystal ball. Okay, but the parametrization, it's the parametrization which is not smooth at 2 points when phi is 0 and when phi is pi. However, there is a however, because the only reason why the length is 0 is because of this pesky factor of sine of phi. It does not appear in this. Well, it does appear, but there is a cosine phi over there. Okay. So therefore, if we go to that unit normal vector and plug in 0 and pi, we don't get the 0 vector because, of course, we're supposed to get a unit vector. If we plug in 0, north pole, that vector is 0, 0, 1. Boom. Okay? Plug in pi, you'll get 0, 0, negative 1. Okay, so that makes sense, right? If you have a sphere, at the north pole, your normal vector is perfectly vertical, 0, 0, 1. If you're at the south pole, the normal vector is going down, 0, 0, minus 1. Okay? So therefore, the conclusion here is that this vector is always going to give you a normal vector to the sphere at the given point on that sphere. Okay, boom. Oh, I guess I just had a message. So that's our video for today. I hope you enjoy it. Next time, we are going to look at a new kind of integral, the surface integral of a scalar function. So until then, I hope you enjoy the rest of the day. I will see you at our next video. Bye.